With things in this one, let's talk about this theorem that says if we have a non-decreasing function f over the real number inputs a till b, so this interval from a to b, a being smaller than b, and by the way, the fact that we label this concrete infimum as L will be more relevant to the proof, so let's keep it away for now. But the rest of the theorem is basically this part. Then we have that if we approach a from the right side, which is the left bound of the limit, from the right side, so limit as x goes to a from the right side, the right limit of x goes to a of f of x of this function we're concerning over the interval a to be non-decreasing. It's actually going to be equal to the infimum of all the function values on that interval. So imagine a function that's non-decreasing. That means either it stays the same or increases. Then if the left on this interval, then the leftmost point of the interval, the left bound of the interval, will be equal to the infimum of all the values of the function. It's quite self-evident if you think about it, but let's anyway go over the proof. So the proof, basically the fact that we took this infimum, okay, so we consider this means basically all the values of f on the interval a till b. The fact that we consider this infimum and label it L is more practical for the proof itself. So perhaps one can write it here, right? So if we start the proof, for sake of clarity, let's label it as such. And we can take a positive epsilon real number, of course, that there can be a y inside the function output values that's strictly smaller than L plus epsilon. And what x will f of x give y for? Well, we can find such x and label it x bar. So some f of x bar will be that epsilon. So we say, okay, we want this infimum, so the smallest, basically the greatest lower bound, which is the definition of an infimum, of all the function values to be L. And if we go just by any positive epsilon real number to the right of it, we're already strictly beyond y. So we want some y that's basically very close to f of a, alright? And what we get is we can find an x bar that fulfills, first of all, this equality. But then also, for every x inside the interval going from the left side of this bound AB over which we have the function f till x bar, f of x is smaller or equal to f of x bar, which might be slightly either same in value or slightly beyond, but strictly smaller than L plus epsilon. And we can imagine and expect L to be very close to A anyway, so this is not a big interval that we're considering at this point. And also for any x inside the same interval, we will have the function value, which is similar to what we stated here. We sort of show that f of x is strictly smaller than L plus epsilon, so we just say here once again. But now we don't not only say f of x is strictly smaller than L plus epsilon, which this would say if we didn't put the absolute value, but we put the absolute value is the same as saying f of x minus L is between L plus epsilon and strictly bigger than L minus epsilon. Because of course, f of x, is at least gonna fulfill, it's not gonna be below the infimum of the function values. So if we go L minus epsilon, so the infimum of the function values on the interval to the left, by epsilon, we're already clearly strictly below that value. So, okay, f of x minus L is between L plus epsilon and L minus epsilon. And another way to say it is, in absolute value, it's below epsilon. And then the final point where we sum it up and get the final conclusion is we can find after this some delta, a real number, higher than 0 again. Similar like all the epsilons and stuff were also positive real numbers. Such that when we take some interval and some anyhow small delta, or any real number delta, so we create an interval from A, so we are looking back at this interval from A to B, going from the left side from A, and it's non-decreasing. So again, let's just keep always throughout this proof the idea that either it stays the same in value or the function goes up in value, it doesn't decrease, alright? So for every x in this sort of interval where we start at A and go by delta to the right only, we don't go to the left, so it's not the full neighborhood to both sides, like A minus delta until A plus delta. But just like here, we start with A and go some delta to the right. It should be, we can find a delta that's that's smaller than the difference between x bar and a, such that this is a subset of a till x bar interval. And then for every x inside this a till a plus delta, which would be a subset of this interval that we talked about before, we have that the values of f of x don't deviate from L. Basically this says similarly like the same like here, don't deviate from L by more than any real number epsilon, so we are very close. And this sort of is the limit definition idea, where f of x is very close to L. Alright, again, another way to write out this is f of x is between L minus epsilon and L plus epsilon. So we got there, we've basically got all the way to the right limit sort of definition, where we have some right neighborhood, so slight interval to the right of A by some real, possibly very small value delta, a real number. In that we have that the value of the function's output will not deviate from L by some perhaps very small epsilon real number. So we got there, and here's the conclusion of the proof. So we went over this idea once again to reiterate it. The idea is basically that we have a function over a non-decreasing interval. The value will stay the same or go up, it won't go down throughout this interval. And we're saying that if we approach from the right side, because we don't know what happens before that interval perhaps, but if we approach, and it's continuous of course, it must be continuous, not like some jumps or something, because then these things would not work out reliably and necessarily. So if we approach the point A, which is the left bound of this interval, from the right side, that's what it says, it should equal to the infimum of all the function values on that interval, which is quite clear from when one thinks about the scenario, but we can also supply proof step by step.